All right, good morning, everybody. Um, Welcome back. It is Wednesday. Hope you guys have been having a great week so far. I want to, again, just as a reminder, tomorrow we're going to be reviewing for the exam on Monday. We're not going to be completely done with Chapter 4, but this seemed like a good place to kind of stop. We have one section left in Chapter 4, but that's something that we can kind of just do and kind of tack on to the stuff that we're doing ahead for next time. Today, what we're going to do is we're going to review what we've talked about so far about substitution. Try to clear up anything that's not very clear right now. And there's a few other things I want to say about substitution, and then I'll give you some time later on today to work on some of those problems related to substitution. So, again, just as a reminder, the fundamental theorem of calculus taught us that if I want to evaluate an integral, particularly a definite integral, the key here is to find an antiderivative. Because if I can find an antiderivative, then I just plug in b and plug in a, and I'm done. So doing definite integrals is really about finding antiderivatives. But one of the things that we've seen is that finding antiderivatives is not as straightforward as finding derivatives. And you saw that in the example, hopefully, that we did last time. So if I wanted the area under tangent from 0 to pi over 4, I need to find an antiderivative. But the tricky thing is that I don't have, unless I know what the answer is. Okay, last time I gave you the answer, it's negative natural log of absolute value of cosine. But you might think, how in the world would I come up with that? You do know the antiderivatives of sine and cosine, but the problem is that we don't have a way to reverse or to, we don't have an anti-quotient rule or an anti-product rule right now. We will be looking at something similar to that later on. But you might actually, well, I won't mention that, but you can actually do this problem with substitution. I want you to maybe think about that, and I might even give you some bonus on the homework if you figure out how to do a problem like this using substitution. So I'll let you think about that. But the moral of the story is that you have to be able to figure out an antiderivative in order to do some of this work. And the antiderivatives are not as straightforward as the derivatives are, because they have to be set up in such a way that they came from a derivative. So kind of as an example of, we looked at one example where if you wanted to do the antiderivative of sine of e to the x dx, we actually could find that antiderivative. That one actually had a nice antiderivative. But sine of e to the x does not have a nice antiderivative. And the difference here is that this one is set up to be the result of differentiation. Okay? It's set up to be kind of a reverse of one of our rules. And we saw that by letting u equal the inner function, and we saw that this thing that ends up out there ends up being the differential. It ends up being the du. So let's do one more example kind of like that before we start throwing in a few other things that are a little bit different. Okay, let's do an example of cosine squared x times the sine of x dx. Okay? Now, if we don't immediately have a rule for it, if the rule is not in that list that I have, and it's not a constant times one of those things or a sum, then I actually have to do some work. And what you'll notice here is that I do have a composition, and the inner function, again, to make sure this is super clear, this notation just means cosine of x quantity squared. So there's an inner function here that is cosine, So if I let u equal that inner function, then the differential du is going to be negative sine of x dx, and you'll notice that that's basically sitting right there. It's off by a negative, but the negative is not going to be that big a deal. I can throw that negative right here, and all is well right there. So what I'm going to do is I'm going to substitute in u equals cosine, and so I'm going to get u squared, and then this sine of x dx is going to be negative du. And that negative can just come out. So we now have an integral that is very easy and is something that I can do. This is 1/3 u cubed. And if I just throw cosine back in, then this is going to be my answer. One thing I have to point out that I don't think I pointed out last time, if your problem starts with x's, it has to end with x's. If you leave the answer here, I will mark some stuff off because the original problem did not start with u's, it started with x's, so my answer should be left with x's as well. Does that make sense? Okay. So let's first ask, okay, we figured out how to do substitution when I don't have limits of integration here, when I'm talking about an indefinite integral. How do I do substitution for definite integrals? And it turns out there's a couple of different routes that you can take here. Okay, so let me give you an example here first. Let's do the area from 1 to 2 under x squared times x cubed minus 1 cubed dx. Okay? So first of all, if 1 and 2 isn't here, this is very similar to one of these previous problems that we were looking at, and you'll notice that I have a composition here, and this thing that's sitting right here is basically the derivative of this thing. Derivative of x cubed is 3x squared. Derivative of 1 is 0, so that goes away. But that 3 is not really going to be that big a deal. Okay? So what I would be tempted to do here is to let u equal x cubed minus 1, and then my differential du is going to be 3x squared dx. Okay? So ignoring the 1 and the 2 for right now, I guess I should say that means that x squared is going to be 1/3 du. Right? Okay, so ignoring the 1 and the 2 for right now, x cubed minus 1 is going to be u, so I've got u cubed, and then the x squared dx is going to be 1/3 du. Okay. Now, the thing you have to be careful of when you do substitution and you're talking about a definite integral, so you've got a 1 and a 2 here, the thing you have to be careful about is what this notation means is we're taking this function and we're finding the area under it from x equals 1 to x equals 2. And the reason I know that's x is because of this variable that's being used right there. So if, for instance, I were to write down u cubed times 1/3 du, and I were to write a 1 and a 2 here, that would actually be wrong. And the reason is that this is not u equals 1 to u equals 2, but that's what I'm implying when I write a u here, du, and then I put numbers here. That means I want the area under this function from u equals 1 to u equals 2. That's not actually correct. Okay, when x is 1, u actually is not 1. And when x is 2, u is not 2. So this would not be correct. So there's a couple of things that I can do here. One way to deal with this is that when I substitute, I can simply write, keep the limits of integration the way that they are, And I can write x equals 1 to x equals 2. And that's just a reminder that those numbers, eventually when I substitute, I have to substitute for x's. So let me show you how this would work. If I leave this with x equals 1 and x equals 2, again, we pull out the 1/3, and I need the integral of u cubed. So the antiderivative of u cubed is 1/4 u to the 4th. Okay, I don't need the plus c because we're talking about definite integrals here. And now what I'm going to do is substitute back to my x's. So I've got x cubed minus 1 to the 4th. And now I can just write 1 and 2 because my variable here is just x. So I can just write that I'm going to plug in 2 and I'm going to plug in 1. Does that make sense? So I keep these limits of integration in terms of x until I get all the way to the end of the problem and I've come back to x's. And then I just substitute in 2. So 2 cubed is 8 minus 1 is 7. So I'd have 7 to the 4th minus, if I plug in 1, I get 1 cubed is 1 minus 1 is 0. So that's just 0. So I would get 7 to the 4th, whatever that is, over 12. Okay, that would be my answer. That's one way to do this problem. Okay, does that make sense? So I keep my limits of integration, which truly are about x's. I keep them all the way to the end. When I get back to x's, then I sub in. The other way that you can do this problem is when you do the substitution, you do it over here, and I let u equal the inner function, so I get u cubed, and right here I get 1/3 du is x squared dx. So this is 1/3 du. What you can do is instead of keeping x equals 1 here and x equals 2 here, you can just substitute in completely for the limits. So when x is 1, u would end up being 0. And when x is 2, plugging 2 in, 8 minus 1, u would end up being 7. So what I've done here is instead of keeping the limits in terms of x, I substitute the limits as well. Now let's check and make sure that we actually get the same answer. So if I pull the 1/3 out, the antiderivative of u cubed is 1/4 u to the 4th. So I get 1/12. And now you'll see that when I'm plugging this in, I'm going to get exactly the same answer that I'm getting down here. When I plug in 7, I'm going to get 7 to the 4th. When I plug in 0, I'm just going to get 0. So I get again the same answer that I had over there. So that either one of these techniques is correct. You can do either one. People generally go toward this second technique because notice I didn't have to go back to x's. It actually shortens my work. You can actually see that the amount of work that I had to do is less here. Less writing, less work, because I can just substitute immediately in for u's rather than going back to x's and then substituting. But either one of them is fine, and I'll show you when I work a couple of examples, I'll try to do both so you can see both. Okay? All right, let's take a look at another example here. All right, let's do the antiderivative from 0 to 1 of sine of e to the x times e to the x dx. Okay? So again, I see a composition here. So let's let u equal e to the x. Du is going to be e to the x dx, which is exactly what I want. Let's do this first technique here. So let's substitute. I'm going to keep my limits of integration according to x's. But I see the sine of u, and then this other part right here ends up being the du. And the antiderivative of sine is cosine, except my derivative is going to give me a negative, so I need a negative there, compensating for that. And because these are in terms of x, I need to go back to x's. So I'm going to put my e to the x back in, and now I can just write from 0 to 1 because that's the variable there. So what I'm going to have is cosine of e to the 1 minus negative cosine of e to the 0. And e to the 0 is 1. So I get negative cosine e plus the cosine of 1, whatever that is. Okay? Alternatively, what I could have done here is I could have said that this equals, and I substitute in sine of u, and then the du. But I also say when x is 0, what is u? Well, e to the 0 is 1, so u is going to be 1. And when x is 1, e to the 1 is just e, so u is going to be e. So now I've got everything substituted, so when I come in and get my antiderivative, I can just plug in e minus plug in 1. And I get the same answer. Okay, again, most people are going to prefer substituting everything. There are a few situations where you actually don't want to do that, but most of the time you are going to want to do that. Okay? Does that make sense? All right. Let's try one more of those definite integrals. I think this time I'm just going to do the total substitution method. If you want to keep it using x, you can do that. That's fine. Okay, so let's do the antiderivative from 1 to 9 of 1 over the square root of x times 1 plus the square root of x squared dx. Whew. I kind of want to do this problem in part because the substitution part of it is kind of interesting here. So I want you to talk to the person next to you just for a second and see, can you see a composition there? Do you see a composition happening there? Okay, those parentheses should be an indicator. This seems to be the composition. Okay, so if we let u equal the inner function, okay, I've got that thing squared. Du is just going to be the derivative of this. Derivative of 1 is 0. And the derivative of x is x to the 1/2, so it's going to be 1/2 x to the minus 1/2 dx. In other words, it's 1 over 2 root x dx. Do you see anything in there that looks kind of like that? You should. This 1 over root x right here is actually part of that, and it's actually cooked up that way. It's supposed to be there on purpose. Okay, so if I move this 2 to the other side, I've got a 1 over root x dx, and that's actually that part right there that I've just circled. So if I do my substitution now, I've got 1 over this thing, u squared, and the 1 over root x times the dx becomes 2 du. Do you see that? Do you see how that ended up being came out really nice? Now, let's go ahead and substitute the limits too. I could write x equals 1 and x equals 9 here and carry that all the way down, but then I have to sub back in. I don't want to do that. So when x is 1, u is going to be 2. And when x is 9, the square root of 9 is 3. 1 plus 3 is 4, so u is going to be 4. So now I don't ever have to go back to x's again. Okay, so this is going to be 2. And then I've got u to the negative 2. So the antiderivative of u to the negative 2 is going to be u to the negative 1 over negative 1. Okay, so in other words, it's going to be negative 2 over u. And we're going to plug in 4. So if I plug in 4, I get negative 2 over 4 minus plug into negative 2 over 2. So I've got negative 1/2 plus 1 is 1/2. And that's my answer. All right, so that gives you an idea of how to do this. Sorry, my computer went off. How to do this when we're talking about definite integrals now. Let's do a couple other examples that are a little more difficult, where we're going to have to do a little bit more manipulation to be able to do substitution. So let me give you an example of what I mean here. Let's do the antiderivative, the indefinite integral of x root 2x minus 1 dx. Okay? Now, there should be a clue here that I want to do substitution. I see a composition, and my inner function is that function right there. So if I let u equal my inner function, du is going to be the derivative of this function is just 2 dx. Okay, so I see a dx there. So I can bring that 2 to the other side. So I can substitute for this just fine. This is going to be root u. And I can substitute for this fine. That's just going to be 1/2 du. This x is a different story. This x is a little bit different. But I can actually substitute in for x by taking this equation right here and solving for x. Notice that I can add 1 to both sides, and then divide by 2 or multiply by 1/2. And I end up getting an expression for x here, and I can substitute that in right there. So if, for the x, I put in 1/2 u plus 1, and then for this is going to be the square root of u, and then the dx ends up being 1/2 du. Okay. Please note you cannot do the following. You can't go like this. You can't just leave the x there, substitute in for the u there, and substitute in for the u there, and just try to go on your merry way. You can't do that. If you're going to substitute in, all of that variable has to go away. You have to get rid of the entire thing. You cannot do that. You have to figure out a way to get x in terms of u. In this case, that's not all that difficult, turning x into a function of u. I can pull out both of those halves, and you'll notice that I now have u plus 1 times the square root of u du. And this should now remind you, I don't have an inverse product rule, but I can multiply these out. And then I get something, u to the 3/2 and u to the 1/2. Both of those things are things that I actually can anti-differentiate. Okay, so let's go ahead and do that here. So we've got 1/4. Antiderivative of u to the 3/2, that's going to come from u to the 5/2. We reduced the power by 1. So in order to avoid that 5/2 from coming out front, we've got to multiply by 2/5. U to the 1/2 came from u to the 3/2, and we needed 2/3 right there. Don't forget your plus c. And now we just substitute back in for what u actually is. Okay, 1/4. 2/5, 2x minus 1 to the 5/2 plus 2/3 times 2x minus 1 to the 3/2. Okay, and if you were to differentiate this out, it would collapse down and you would actually get that answer. Believe it or not. Okay. All right, so sometimes when you try to substitute, you're going to get something weird there that you have to solve for x or solve for something in order to in order to do a little bit more work. Let me give you another example here. Let's do, question is how hard do we want to make this? Yeah, let's go ahead and do something. So let's do x to the 5th root x cubed plus 2 dx. Okay. Now again, the sign to me that I need to do substitution here is my composition, and I'm going to let u equal that inner function there. All right, so u is my inner function. If that's true, then du is 3x squared dx. Now I don't have an x squared, but I have an x to the 5th, so I kind of do have an x squared, right? This thing, if I were to kind of rewrite it, let's separate it out into x cubed and x squared. I do have an x squared dx, right? So thinking of that, let's put the 3 on the other side. That becomes my 1/3 du. So this I can substitute for. That's going to be root u. And this thing over here is going to be 1/3 du. But I've got that pesky x squared, x cubed sitting here that I haven't substituted for yet. How am I going to get rid of that? Well, what I need to do is I'm going to have to solve for x cubed. And what I notice is that u minus 2 is x cubed. So I can put in for the x cubed, I can put that as u minus 2. X squared dx is going to be my 1/3 du. And then this root is just going to be root u. Okay. And you see that this one's actually much simpler than the previous one because I can take that root u times u and get u to the 3/2 minus 2u to the 1/2, and each one of those things is something just like over here that I know how to anti-differentiate. Okay, again, I'm going to get 2/5 u to the 5/2 minus 2 times 2/3 u to the 3/2 plus c, and now I just substitute back in. Again, don't leave it here. You got the integral done, and you're tempted to say, oh, I'm done. But you got to substitute back. If you don't substitute back, it's not correct. Okay, so I've got to write x cubed plus 2 to the 5/2 here, and then x cubed plus 2 to the 3/2 there. Got it? Okay. So that's another thing that can happen. You may have to solve for something in one of your integrals. Okay. Let's take a look at a couple of examples that are a little bit more tricky because the composition is hidden. Okay. Let's take a look at, for example, there's two kind of classic examples that I've seen where people go, I don't see the composition. Okay, natural log of x over x dx. There really isn't a clear composition here where you can let u equal an inner function. So my question is, do you see, though, a substitution that you could make? I want you to think about it for a second. What's a substitution you could make there, and why? Think about that for a second. There's a way to rewrite that makes this a lot clearer what the substitution would be. If you catch it, then you're going to see what substitution you need. So the two things that my recommendations before, the things that you want to look for when you're looking for doing substitution, you're looking for composition, and you would let u equal the inner function. The other thing that you're looking for is what I call looking for the du. You're looking for the thing that's a derivative of something else in the integral. So as an example, you'll notice that x squared is basically the derivative of x cubed. It's not quite, it's off by a constant, but constants are not that big a deal for us. Okay, so if the du, if x squared is the derivative, it came from x cubed, and that's the clue to me that I probably want to let that x cubed minus 1 be my u, and then the x squared is going to end up being my du. Do you see anything in here that looks like the derivative of something else in there? Okay, if I rewrite this as natural log of x times 1 over x, then I kind of give away my hand. Okay, notice that 1 over x is the derivative of natural log. And if you notice that, then you could start by saying, oh, if the du was 1 over x, then it came from u equals natural log. So you can kind of sometimes backtrack to figure out what your u should be based on the derivative that you're seeing. Does that make sense? So here, the natural log would end up being u, and the rest of it would end up being du, and you would just get 1/2 u squared. In other words, 1/2 of natural log squared. And if you differentiate this, you actually are going to get that answer. Does that make sense? So sometimes in your substitution, you're looking for a composition, but sometimes the composition is not completely clear. So sometimes you're looking for a du. Let me give you another example here. Okay. So in this example, you might think I've got a 1 over 1 plus x to the 4th. So if I were to let u equal 1 plus x to the 4th, my du is going to be 4x cubed. Now what's the problem there? I don't have an x cubed sitting up here, x cubed dx. I don't have that. I only have an x dx. So this actually won't work. Can you think of a different one? Well, if you look for the du here, if you think of the top being the du, again, we don't really care about constants. What function does x come from as the derivative? What would I differentiate to get x? Well, I would differentiate x squared, right? And if I differentiated x squared, I would get 2x. So let's see what happens if we do this. Now I only have x dx, so I have to put a 1/2 out front, but that's not a big deal. So what I have here is that this integral, the x dx is 1/2 du, and the bottom is 1 plus x to the 4th. How is x to the 4th related to x squared? Well, if I think of x to the 4th as x squared squared, that bottom is going to be u squared. So in other words, I need to find the antiderivative of 1 over 1 plus u squared. What function do you remember when I differentiated it gives me 1 over 1 plus something squared? Remember that function? We had an inverse trig function that did that. That is arctangent. Remember that? So, and u is actually x squared. So this turns out to be, the antiderivative here is 1/2 arctangent of x squared plus c. So here, in this problem, the composition was actually hidden. The composition looked like this. But you didn't see it because somebody collapsed the x squared squared into x to the 4th. If you were to see this, you could think, oh, let's let x equal u equal x squared, and du, the top is going to then be the du. But if you don't have that, you have to kind of backpedal. You have to figure from the front backwards. If the dx is this, if the du is this thing right up here, what was the original u? Does that make sense? Okay, now that's about the hardest type of example that would come up here, but it's a subtle example that I think it's important to understand. You're really looking for two things. Composition, if you find that, let u equal the inner function, or looking for the du, looking for the derivative of something else in the integral. Okay, one last thing that I want to present here, and it's actually kind of a useful technique, and it has to do with even and odd functions, okay? This is a very, very special situation where you can use this, but substitution is going to allow us to prove this. So I want you to notice, so let's maybe recall for a second, that a function is odd. When we say a function's odd, visually what that means is that the left side and the right side look the same if you spin, the function looks the same if you spin it around the origin. In other words, if I spin it 180 degrees around this point right here, around the origin. So if this function looks the same if I turn around and look at it upside down, then it's odd. Algebraically, what that meant was if we plugged in negative x, what we would get is the negative of the original function. So for instance, x cubed works this way. If you plug in negative x, you get the negative of the original function, negative x cubed. And x cubed looks the same if you flip it 180 degrees. Okay? If we are talking about an even function, that looks the same on if we reflect it around the y-axis. Okay, so that's the visual. When you plug in negative x, it turns out it doesn't change the function. You get the original function back, and that's true for even powers of x, like x to the fourth. If you flip it around, it looks the same, and when you plug in negative x, you still just get x to the fourth. Okay. It turns out that if you pick any number on an odd function and go from negative that number to positive that number, can you see what's going to happen with the area here? If on an odd function I go from negative a to a, what's actually going to happen there? Can you guess? Looks like if I go from negative a to a, the area over here that's positive is going to be canceled out by the area over here that's negative, and the area should end up being 0. Whereas over here, if I go from negative a to a, just from some point to it's negative, it's not going to cancel out. If this side's positive, this side's also going to be positive, but you'll notice that if I go from negative a to a, that's really just 2 copies of going from 0 to a. Can you see that visually? So if I do, again, for the odd functions, if I go from negative a to a, I've got negative on one side and positive on the other. Those areas should cancel out. But if I'm talking about an even function, and I go from negative some number to positive that same number, I really only have to do half of the work and then multiply by 2, and that's going to give me the area on the other side. The reason this is nice is that plugging in 0 is always a nice thing to do with functions. So if I can plug in 0 instead of plugging in negative numbers, that's ideal. So it turns out that both of these things are actually true. These two properties are actually true, and the way that we prove it is using substitution. So let me show this to you real quick. You don't have to write this down. I'm not going to test you on this, but these two properties are actually really, really useful for calculating integrals, especially this one. If the answer turns out to be 0, we want to know right away. So let's take a look. Let's do the integral from negative a to a of a function. If I were to do this, what I'm going to do is split it and go from negative a to 0, and then from 0 to a. Okay. And then what I'm going to do is in this first integral, I'm going to do a substitution. Now you might wonder, why in the world would I do a substitution? Just roll with me here. Let's let u equal negative x. So in this case, x is negative u, and dx is going to be negative du. So this is just in that first integral. So what I'm going to do is I'm going to say now, I'm going to get f of x, well x is negative u, so f of negative u, and then dx is negative du, and when x is negative a, negative a, u is going to be a, and when x is 0, u is 0. Okay? We good so far? Of course, my computer goes to sleep again. All right. Okay, the second just comes along for the ride. So now, what I'm going to do, let's flip these, and if I flip the limits of integration, I get another negative sign there. Okay, and this negative sign is going to cancel that negative sign. All right, so now this is where I do a couple of cases. So if we're talking about an even function, so if f is even, then if we're going from 0 to a, f of negative u is just f of u. Okay, so f of negative u, and f of negative u would just be f of u. Now, this is just a number, and this is just a number, and it doesn't matter what letter I'm using. I could write f of u or f of x here. So these are actually just two copies of each other, and so this turns out to be two copies of the area from 0 to a, which is what we wanted to prove up here. Okay, so in the case of an even function, this actually works. In the case of an odd function, f of negative u is going to be negative f of u. So we get negative f of u du. And what ends up happening here, again, it doesn't matter if I'm talking about u's or x's, this is a number, and this is that same number, and they have a negative on them, so they end up canceling one another out, and I just get 0. So in the case of an odd function, if you're going from negative a to a, so in other words, if I was going, for instance, from negative 10 to 10 under x cubed, that's just 0. It's an odd function, and we're going from negative a number to positive that same number. It's critical, though, that these numbers are negatives of each other. You can't go from like negative 10 to 8. This doesn't talk about that at all. Okay. It's also critical that the function's either even or odd. If it's neither, then you're stuck and you can't do anything. Okay. All right, so hopefully this should still give you some time in class to work on some substitution problems. Ms. Barbo is there to help you if you've got any questions. We'll review for the exam tomorrow. We'll talk about what problems are on there. I'll post the solutions to the review problems. So you've got those solutions to look at over the weekend, but please try to work through those problems on your own first. Don't just copy the solutions down. That's not going to help you. It'll help you a little bit, but it's not going to, you're going to get a whole lot more benefit trying to do the problems yourself and then going, I don't remember how to do that. Maybe looking back at your notes, trying it again, and then if you totally get stuck, you can look at how the solutions go. Okay? So I will see you tomorrow. Have a great day.